29 and I find myself wondering, what did happen to the last 10? I ran away with my life, fast forward, never turn back again. It's kind of funny that the more we pass time, the more we need to set them rewind. And 19 was the year I had to leave you, but now I'm seeing all the signs. Is this really happening? I can't believe it's true. I'm just as surprised as you. Is this really happening? I can't be too sure, but one day I'll be yours again. Life lessons come one in a dozen. The other 11 give something from nothing. I sit here looking for an answer. Maybe the biggest question was in the last chapter. You gave me the soul I have today. Without you I never could have moved away. But now I see what you teach. I do believe I always should have stayed. Yeah. Is this really happening? I can't believe it's true. I'm just as surprised as you. Is this really happening? I can't be too sure, but one day I'll be yours again. One day I'll be yours. One day I'll be yours. Life lessons come one in a dozen. The other 11 give something from nothing. Life lessons come one in a dozen. The other 11 give something from nothing. Life lessons come one in a dozen. The other 11 give something from nothing. Life changes just open the door. One thing's certain, I'll always be yours. Is this really happening? I can't believe it's true. I'm just as surprised as you. Is this really happening? I can't be too sure, but one day I'll be yours. Yeah. Is this really happening? I can't believe it's true. I'm just as surprised as
Godspeed to the city streets. We began to feel the fire. We rise like tall buildings as the chemicals, they take us higher. The night's young and it's just begun as she puts her hand in mine. We wanna chase the night, wanna dance to the light, pull the stars from the sky, just two hearts running wild. Never sleep, never stop, as we shout from the top. We're gonna be two hearts running wild. So loud as the hours pass, we're gonna do it all again. We wanna chase the night, wanna dance to the light, pull the stars from the sky, just two hearts running wild. Never sleep, never stop, as we shout from the top. We're gonna be two hearts running wild. The moonlight, summer sky, it was the best we ever had. And we'll stay on forever. We'll never have regrets. We wanna chase the night, wanna dance to the light, pull the stars from the sky, just two hearts running wild. Never sleep, never stop, as we shout from the top. We're gonna
Hello, Professor Picarotti. Yeah, Sucha is my name. Did you see me?
Yes.
Yeah, thank you very much for you accepting our conference. I will join in to your presentation.
It was a pleasure. Yeah, it was a pleasure, and I'm sorry not to be able to be there in person, but this period is very crowded of several meetings and projects, and
Yeah, but
share the
thank you very,
yes.
very much anyway.
I will,
In the future, I
will
hope that we have opportunity to welcome you at KMUTNB.
Thank you. I will come with pleasure. Thank you. Yeah.
I know your name as well from my former doctor father, Professor Karl Kosich. He was my
Yes.
professor in Germany.
I remember Joseph very well. He came to Trento several times, and I also
he talked it many times about you to me.
Thank you.
Okay, thank you. No.
Welcome back once again for the keynote talk in the evening session. I now invite Dr. Mohit Kumar, a research scientist of KMUTNB and technical chair of this conference, to introduce our keynote speaker.
Thank you, Mr. Esigo. Good evening, one and all. Professor Dr. Alexandro Pegretti from University of Taranto, Italy, is our keynote speaker for this evening. Professor Dr. Alexandro Pegretti graduated in Materials Engineering at the University of Taranto, Italy in 1988. After a professional experience in industry, he joined the University of Taranto as an assistant professor in 1992. Between 1995 and 1997, he has been visiting research scientist at the Institute of Material Science of the University of Connecticut, USA. Between 1997 and 2001, he has been aggregate professor at the University of Modena, Italy, and then associate professor and full professor of material science and technology at the University of Taranto, Italy in 2022 and 2012 respectively. From 2012 to 2018, he has been the director of doctoral school in materials, mechatronics and system engineering of University of Taranto, and since 2021, he is the head of Department of Industrial Engineering of the University of Taranto. From 2022, he is the editor-in-chief of Polymer Composites, the Engineering and Scientific Journal of Society of Plastic Engineers, serving the fields of reinforced plastics and polymer composites. He has authored over 330 referred publications, 2 books, 15 book chapters, and 3 patents on various subjects in polymer and composite science and engineering. I now wholeheartedly welcome Professor Dr. Alexandro Pegretti to deliver his keynote speech on functional interfaces for structural composites. Over to you, Professor.
Okay, thank you. Can you hear me, and can you see the screen?
Yes, Professor, we can hear you.
Okay, thank you very much. And I also would like to thank you very much the organizer of the conference to invite me. It's really an honor to share this piece of research with you. So the aim of this presentation is to try to give some overview of some recent activities we have been doing here at the University of Trento in the field of functional interfaces for structural composites. So after a brief introduction, I will describe the aim of the study, and then I will focus the attention on 2 main topics. One is how we can improve the fiber matrix interfacial adhesion, and by relatively new techniques. One is the deposition of nanostructured graphene on fibers, in particular glass fibers. And the second one is how we can treat the surface of fiber by laser.
Next, I will move into a more recent field in which we are trying to develop a self-healing capability at the fiber matrix interface in order to restore the initial adhesion after a failure in this region. And in this field, we are trying to either deposit thermoplastic nanoparticles or to deposit a continuous film of thermoplastic polymer on the fibers. And finally, I will draw some conclusions. The field of composite material, needed to say, is very, very important for several reasons. In particular, we know that this kind of composite materials, they can compete with metallic and ceramic materials in terms of mechanical properties, but at the same time, they have a much lower density. So the weight is for sure an advantage in comparison to steel or other metallic materials. Also, in terms of property, they have high stiffness, strength, and fatigue resistance. So these are the main reason why we're using them. And what we can do at this point is to look at the market, which is very extended. We have reached so far worldwide a market estimated in 12.7 million tons, which means in terms of money about 40 billions in terms of material, pure materials, and in terms of components, we can exceed $100 billion, which is really a huge market. This picture is actually one of the main or the most well-known pictures you can find in the literature regarding the interface. So basically here you can see how complex is this region, and this picture was taken from a paper by Drasal of more than 40 years ago, but it is still very, very actual in terms of the pictures. And the reason of this complexity is basically related to the very large number of interactions that can occur in this region. We can have macromolecular interdiffusion, chemical bonds, electrostatic attraction, and also some mechanical interlocking like frictional and thermal contraction. The interface tailoring may be a touch from 2 points. One is either to work on the matrix, like to modify the matrix, like to disperse nanofillers in the matrix, for example, or to make a nanostructuring of the bulk matrix. And or we can work on the fiber surface, and this is actually our approach today. In this field, we can use several types of approaches. Surface chemical treatments are the most common, by using silane, for example, or titanate. But we decided to focus our attention on more advanced type of approaches, in which we are using either nanofillers deposited on the fiber surface, laser treatments, as I mentioned before, or the deposition of polymeric nanoparticles or film coatings directly on the fiber surface. The aim is to, as I mentioned before, to improve the properties, mechanical properties of the interface, but also to bring in the composite material some, let's say, multifunctional characteristics. For example, we can aim to improve the energy absorption, or to use the composite material to sense and to detect vibrations, for example, or mechanical strain, or as I will show in this presentation, we can use this composite material to repair basically some damages during the exercise. For us to serve sensing and damping, there are various examples. One possibility, which is something we explore, is to make insulating materials like epoxy glass fiber to be conductive by a proper sizing, by a proper coating on the fiber. And in this case, you can see how we can monitor the stress, for example, by following the change in the resistance. and this can be useful to monitor the stress also under dynamic conditions, like in fatigue experiments or in a real situation. And this is one of the possible way we can induce multifunctionality in composite materials. Self-healing is also another subject that we investigated, and there are basically two main approaches. One is the so-called extrinsic self-healing system, which is based on a reactive system, basically like capsule, which can be dispersed in the matrix, and they can heal the fracture in case of need. Or we can use a so-called intrinsic system in which some reversible physical or chemical interaction may be exploited in order to make this healing to be repeated over the time. And this is actually the approach that we follow. So we are basically working in this intrinsic healing. And one of the approaches which is mostly used today is to disperse plastic material healing agent in form of particles, for example, in the polymer matrix. And what we did is to use the same approach to coat the fibers with a layer or nanoparticles of thermoplastic polymer in order to restore possibly the broken interface. As we can measure the interfacial adhesion, there are several techniques. Here in this slide, you can see the most important. And basically, we decided to adopt two of these techniques. One is the so-called micro-debonding test, in which a fiber is basically debonded from a matrix droplet, and we can measure the load needed to debond the fiber from the matrix. And the second one is the single fiber fragmentation test, in which a single fiber is embedded in a coupon of matrix. This system is pulled and then is loaded, and at this point some fractures appear in the fibers, and the size of these fragments is basically an indication of the adhesion. The smaller in general are the fragments, the higher is the adhesion, and therefore it can be used this method to quantify the in fiber matrix interfacial adhesion, as we will see later. The aim of the study is to exploit the potential of fiber-reinforced polymer composites by enhancing their mechanical performance and possibly increasing their durability, safety, and cost efficiency. And the two main targets that we had in this work is to improve the fiber matrix adhesion and to induce self-healing functionality. And here are the examples I would like to show you today. The first area, improvement of fiber matrix adhesion, was targeted in two ways. One is the deposition of nanostructured graphene into fibers, and the second is by laser treatment. Laser treatment are very fast, and this is the reason why we use also this kind of approach. Starting for the first example, the way we proceed is depicted in this slide. So one possible approach is to disperse graphene oxide, to produce graphene oxide first and then to disperse graphene oxide, which is easily dispersed in water, and by an electrophoretic deposition method, we can force these graphene oxide particles to move from the cathode to the anode, and close to the anode we can put glass fibers in form of fabrics or single fibers, which are at this point which is possible at this point to coat them by a layer of graphene oxide. Here you can see the result. We can change the voltage applied in the system, and depending on the voltage, here you can see 7.5 volt per centimeter in this slide. And if we increase the voltage, or if we increase the concentration of graphene oxide in the solution, we can obtain a homogeneous coating of graphene nanoparticles onto the glass fibers. At this point, we use the single fiber fragmentation test with an equipment in our lab in which we can pull the sample containing a single fiber, and we can measure exactly the number of fiber breakage and therefore the length of these fragments. This length is called the critical length, and therefore for the critical length we can measure an interfacial shear strength, which is a quite widely used approach in the literature actually. If we look at the results, you can see how the interfacial shear strength can be really improved, and the improvement is higher and higher when the electric field applied increases. Here you can see two curves. The blue one refers to the graphene oxide coated fibers, and the second one to the reduced graphene oxide coated fibers. Reduced graphene oxide is basically electrically conductive. So this is the reason why we were interested also in reduced graphene oxide, mostly for the monitoring approaches. Of course, the electric field is an indication of the amount of material deposited. In fact, there is a linear relationship between the applied electric field and the rate of weight increase of the fiber, so the amount of graphene oxide that we are able to deposit. For what concerns the functional properties, we produce bulk composites by using these coated glass fibers, and what you can see here is that the electrical conductivity is very remarkable changed. In fact, in case of reduced graphene oxide fibers, we can reach a very low value of the electrical resistivity, which means the material is electrically conductive. On the other hand, the material with the neat glass fiber or the glass fiber coated with graphene oxide are still insulating materials. Here is what I told you before. At this point, we can use this material to monitor, for example, the stress applied to a given piece of a component by very simply monitoring the change in the resistance of the composite material. And this is one possibility to extend the monitoring directly embedding this capability in the material itself. Another type of approach that we follow is not to use electrophoretic deposition, but another technique, which is called triboelectrification. At this point, the technique is to rub basically glass fibers onto a polymer. In particular, we select tetrafluoroethylene, which is Teflon, and by this rubbing procedure, we can charge by triboelectrification the surface of the glass fiber. When you have a charged fiber, the fiber can be conveyed into a bath where we have the solution containing graphene oxide, and this graphene oxide can be attracted by the surface of the fiber, and therefore we can coat the surface of the fiber in a quite similar way. This process has the advantage to be very fast, so we can coat a very large amount of fiber in a very short time. Here you can see basically how the fiber appears after the coating. So basically, again, you can notice the deposition of graphene oxide layer on the surface of the fibers. At this point, we perform the characterization. We decided to use, in this case, the micro-debonding test. And here you can see the configuration. Basically, you can observe the load displacement curve, and the point at which we reach the maximum is basically the point of failure that we can use to compute the interfacial shear strength. The results are quite interesting because you can see how we can really increase the interfacial shear strength, and in the optimal condition, we reach an increase of 45% in comparison to the uncoated fibers, which is a quite good result in terms of improvement of the interfacial shear strength. At this point, I would like just to show you some preliminary results we obtained with the laser treatment. This is a collaboration between a University of Spain, the Universidad de Vigo in Spain, and also some colleagues in Finland at the University of Tampere for as concerned characterization. Here you can see the treatment by laser. You can see the spot which is moving on the surface of the glass fabric. Actually, we treated basalt fibers in this case. And the result of this treatment can be changed by changing the power of the laser. And therefore, you can use different effects depending on the power of the laser. For example, some optical and also some scanning can you okay of basically the effect of this laser treatment on the surface of the fibers. If we exceed with the power, if we use up too high power, we can break the fiber, we can generate holes, or as you can see here, we can also fuse the basalt fibers together. So this is, of course, an indication that the power used was too high. But if we stay in the intermediate power level, we can generate some surface modification. Why we decided to collaborate with the Tampere University? The reason was that these micro-debonding tests are very time-consuming, and at the University of Tampere, they develop an automatic machine that can be used to accelerate the testing. And they are now commercializing the machine to a company which is called Fiberbotics, which is a spin-off of Tampere University. And we are in contact with this company and also with the university, and we are collaborating with them to test this machine. Here you can see a video in which basically the principle of the machine is depicted. So we have to basically hang a single fiber in this frame, and here you can see probably the fiber which is in this region, and here there is a spot of liquid resin, for example an epoxy resin. Here you can see how the fiber can be monitored carefully by a microscope, so you can also in principle measure the diameter of the fiber and align the system very carefully. And at this point we can generate the droplets. So there is a motor which is moving the fiber through a pot of resin. There is a reserve of resin here, a liquid resin, an epoxy resin. And in this way, by tuning the velocity, you can generate very accurate and very consistent droplets. Here you can see the mechanism. The fiber is moving along the bath. Inside the bath, the resin is pooled, and by capillarity, you can see the formation of these droplets. More than one droplets. You can generate a large number of droplets on the surface. Here you can see probably the several numbers of droplets which are generated on the fiber surface, and each of these droplets can be tested. How? The same machine can test the fibers. Here you can see a picture taken by the microscope which is on the machine, and here you can see the droplet. And now I can show you a test in which the fiber is pulled and forced to move through a hole. Here you can see the force as a function of displacement. At a given point, the droplet touches this holder and the load starts to increase. Here you get failure, and then you get friction of the fiber between the fiber and the droplet, which is deposited onto the fiber. In this case, it's an epoxy droplet. So there are two very nice information you can get. The maximum one, the maximum force is used to calculate the interfacial shear strength, and also you get also the friction here, which is an important parameter to be evaluated in composite materials. So this process is automated, so it is very fast, and you can collect a huge number of data points in terms of maximum force as a function of the droplet area. The slope of this curve represents the interfacial shear strength. In fact, the slope is Newton over square millimeter, which is megapascal. Here you can see the effect of this treatment, laser treatment, for example, on the interfacial shear strength. So the increase of the interfacial shear strength is not very clear. We got a slight increase of about 8%, which is a relatively low value. So we are still working on the process to understand whether or not laser treatments can be used properly to increase the adhesion. In the second part, I would like to move to the self-healing, the capability to restore the initial adhesion after the fiber matrix interface is damaged or broken. And in order to do this, we followed two approaches. One was to deposit nanoparticles on the fiber surface, and the second one is to deposit a continuous film on the fiber. We use both glass and carbon fiber for this type of activity. In the first part, I would like just to show you how we obtain a stable suspension of polycaprolactone, which was the healing agent that we decided to use. Actually, this material was very largely used in the literature. There are very nice work by Joseph Carver-Coxis, for example, or Véronique Michaud at the EPFL in Lausanne, in which this material was proven to be capable to heal epoxy resin when dispersed at amount around 10 to 30% by weight. And here what we did was to obtain polycaprolactone PCl nanoparticle dispersed in water, and then by electrophoretic deposition, we coated the glass fibers by these nanoparticles. The nanoparticle suspension was quite stable. We measured the zeta potential, which indicates a stable condition, and the size was less than 100 nanometer, the size of the nanoparticles, I mean. Here you can see basically the pictures of the polycaprolactone coated glass fiber and also carbon fibers. We use both type of fibers in the study. And by tuning the voltage in the electrophoretic deposition process and the concentration of nanoparticle in the solution, we can tune the amount of nanoparticle deposit on the fiber surface. Again, we use, in collaboration with the University of Tampere and the device I showed you before, the microdebonding test to check the healing efficiency. And the healing efficiency is basically measured like the interfacial shear strength of the healed system over the interfacial shear strength of the virgin, the original system. The healing was performed by treating the broken samples at 80 degrees C for half an hour. Why 80 degrees C? Because the melting point of polycaprolactone is around 65 to 70 degrees. So at this temperature, we are at a temperature which is higher than the melting point of the polycaprolactone. So we can induce a flow of the polycaprolactone in the resin and a possible healing. Here you can see the results for glass fiber. In principle, you can see that how the interfacial shear strength was increased by the deposition of polycaprolactone on the surface of the glass fiber, and after the fiber matrix interface was broken, we can restore somehow the mechanical properties to a level of about 50%. So the healing efficiency was about 50%. Of course, without polycaprolactone, the healing efficiency is zero because we cannot restore a thermosetting resin by this very bland thermal treatment. If we look at carbon fibers, in this case, the deposition of polycaprolactone actually decreased the initial adhesion between the carbon fiber and epoxy, but we were able to completely restore the initial adhesion. So the healing efficiency was around 100% in this case. Another type of approach that we used was to use the same materials, the same epoxy resin, the same glass fiber, and the same polycaprolactone, but in this case, we target to reach a continuous film coated on the glass fibers. So not to use nanoparticle dispersed, a continuous film, a continuous coating. This work was published this year in January in Composite Science and Technology, and I would like just to share with you some of the main results. So how can we reach a continuous coating? Well, this process can be reached by tuning the speed of pulling a fiber through the bath. In this case, the bath contains polycaprolactone dispersed in a solvent. And by a proper velocity, it is possible to obtain a continuous coating. And this was actually reached. Here you can see the picture of the fiber, the glass fibers, coated at different speeds. And when you exceed a given speed, a droplet starts to be formed. But this is something we have to avoid in this case. We want to use a homogeneous and continuous coating. After the coating was realized, we deposited the epoxy droplets on the surface. This epoxy droplets is depicted here in yellow. And then by using the machine I showed you before, in collaboration with the University of Tampere, we did a very large extended characterization by testing 30 to 40 droplets for each fiber. So it was a very large number of experiments, but that was possible to be done due to the fact we use an automatic machine. At this point, here you can see the results in terms of interfacial shear strength. Depending on the speed of the coating procedure, you can basically slightly increase or the initial adhesion, but this was actually not the main aim of this treatment. The main aim was to induce healing. So the healing efficiency was evaluated in the same way like before. So we did a thermal treatment, 80 degrees for 1 hour in this case, and we evaluate the healing efficiency as the ratio of the interfacial strength of the heated system over the virgin one. And these are the results. So the healing efficiency in terms for 3 different systems, 3 different velocities. Let's focus on the middle one, which are 3 millimeter per second, which means basically 3000 micron per second. This is the pulling speed. And in that case, healing efficiency of 100% was possible to be reached after the first healing. Next, we also try to repeat the healing procedure in the second and in the third. We break the interface again in a second time and a third time. And as you can see, the healing efficiency was lower in that case, 56% and 52% respectively in the second and third healing. We also try to understand why we get this decrease in the healing efficiency after repeated test. And in order to get information on this, we basically perform a finite element analysis of the system, in which we model the glass fiber, the presence of a coating on the glass fiber, which was a polycaprolactone coating, and then an epoxy droplet on the top, the blade used for basically the micro debonding test is also represented here. And by using this relatively simple model, we try to understand how the shape of this droplet can influence the measured value of the interfacial shear strength. Here you can see some pictures taken during the test. These are experimental results. As you can see, the shape of the droplet changes very remarkably. Here is the position of the blade. And this has to be somehow taken into account in the modelization of the system. If we take this into account, we can see how the maximum force is naturally increasing due to the change in this geometry. So basically, this is captured by the finite element model, and what we have to do at this point is to take this into consideration. So basically, this is something that we can implement in the model in order to take into account the real shape and the real distribution of the stresses in the droplet, which is not considered in the initial evaluation. Okay, so this actually briefly brings me to the conclusions, and what we can conclude is that it is impossible to improve the interfacial adhesion by coating or depositing nanocoatings. In particular, we increase the adhesion by electrophoretic deposition of graphene and graphene oxide on the surface of glass fibers by a very large amount, more than 300% in terms of interfacial strength. And some initial results on laser treatment proves a very much lower increase of the interfacial strength, but still we are convinced that we can use this laser treatment to optimize the effect. For us concerned, interfacial self-healing, what we can say is that it is possible to heal completely a broken fiber matrix interface by the deposition of polycaprolactone nanoparticles or a continuous film coating. And this was reached with carbon and glass fibers in an epoxy matrix. I would like just to thank my group. This basically is a picture of some of the components of the group. In particular, I would like to thank Laura Simonini, who was a PhD student and now is a postdoc in my group, and also Haroon Mahmoud, who also was a PhD student and now is a researcher here in the department. And I would like also to thank the Air Force Office of Scientific Research for the grant you provided for this research, and also all of you for the kind attention. And I'm available here for questions, if any. Thank you.
Now the floor is open for discussion. Thank you, Professor, for such a wonderful talk. I know that many attendees, including myself, left with a great appreciation for the topic and its importance. I am grateful to have the opportunity to hear from you and learn from your wealth of knowledge and experience. Thank you so much, Professor, once again.
Oh, thank you. It was really my pleasure, and I'm grateful that you did appreciate this activity. We are still proceeding with this. Now we are also trying to use different healing agents because polycaprolactone was very largely investigated, and one ideal candidate for this application should be a semi-crystalline polymer and with a low melting point. So this is not easy to be found and also good mechanical properties. So we are now looking for possible alternative to polycaprolactone. One of the limitations of polycaprolactone is it has a melting point of 65, so it cannot be used to heal, or better, if you want to heal a high TG epoxy resin, for example, we have to cure the epoxy resin at very high temperature, let's say 140, 150 degrees, and at this temperature, the polycaprolactone degrades, and therefore we have to look for possible alternatives.
For sure, Professor. Thank you so much for this wonderful sessions once again.
Thank you. Thank you, and I wish you all the best for the remaining part of the conference, of course.
Thank you, Professor.
Okay, thank you. Bye-bye.
Thank you, and all present here. And we will now move on for the lab visit. and we will have the university grand dinner at around 6 o'clock near the STRI building. He gone, professor. Okay.